Um, okay, so any questions about the test tomorrow or homework or anything else? Yeah. Yeah, so I guess I didn't say that. So it's open book and open notes. You can use a computer to look up programs and stuff, but not to like chat with friends or something or to Google for answers. But if you've got like, I don't know, the ebook or something, or you want to look up your programs, then yeah, using a computer is probably the way to go. And then essentially it covers everything, including if statements. And so we're going to get into random numbers today. So everything from random numbers and onward won't be on it. So essentially everything up to and including if statements. And the switch statement, kind of, which we'll talk about next. But I won't. You could use the switch statement, but I won't ask a question about it. But you could use it in your answer if you want. All right. Any other questions? Okay. So once again, it should be pretty. It's pretty fundamental. So the kind of philosophy here is the exams are like base level, and then more of the advanced stuff is coming in the programs for you to write for the homework assignments. And so you'll see that as we get to the last couple. So the last ones will be a little more advanced than the ones so far. All right, so we've been talking about if statements and if-else statements, and we ended last time saying that you could put an if statement inside another if statement. So here we had if y is false, then we had inside that an if-else statement. So when you do that, it's called a nested if statement. Here it's probably worth pointing out that when you have these nested if statements, you could do the same thing without nesting, but maybe the logic may or may not be messier. So for example, the same thing over here could have been rewritten as, let's just do something in here, just say A, this becomes B. So this A and B is just a placeholder for whatever would go inside those curly braces. So here we can see that A would happen if Y is false and Z is less than 50. So those are the two things that would happen for A to occur. And so we could have rewritten this as if Y equals false. Another way you could rewrite this would be if exclamation mark Y. So if we recall, exclamation mark is the not operator, and then that gives you the opposite of whatever Y is. And so if Y is false, then not Y would be true. So this would be equivalent to if true. And then if Y was true, then not Y would be false. So this become if false, and then it wouldn't do it. So this is the same as if Y equals false. So we could do that if not Y and Z less than 50. So if those two things happened, then A would happen. And then, well, when would B happen? B would happen if Y was false, but Z was not less than 50. So then I could do an else here. Not Y and Z greater than or equal to 50. B. And then that'd be it. So here we got rid of the nesting. So we don't have an if inside an if anymore. We just have an if with an else if. So some people might like this one better because it doesn't have the nesting. But it did mean we have a little more complicated stuff inside the Boolean expression for the if statement. If I had written the second one as just else without the else if, this wouldn't be the same logic, because now it would come in here and it would do the else if Y is true. So if Y is true, then this would become false, and it would just drop down here and do B. But that's not what happens here. If Y was true, it would just skip all the way down to what comes afterwards and wouldn't do B at all. So you only want to do B if Y was false, but Z is not less than 50. Okay, so any questions about this idea, about how you can do nested to flatten them? But all right, so here are some really common bugs that occur when we have if statements. And the first common one is using equals equals instead of equals, is using one equal sign instead of two equal signs. So one equal sign we use for assignment, like x equals 1. Two equal signs you use for comparison, like x equals 3, to compare if x is the same as 3. So the good news is, if you use one when you're not supposed to, then you'll probably have a compiler error, so it just won't compile. So if I try to do this, if x equals 1, then do stuff, then the compiler will complain and say you're not allowed to assign, whatever. I'm not sure exactly what it'll say, but it'll say something about you can't do this. So hopefully that'll jog your memory when you see this to say, oh yeah, okay, I need to have two equal signs there to see if x is equal to 1. And then it's pretty uncommon for you to do this the other way. So the other way would be you meant to write x equals 3, but instead you wrote x equals 3. Then I think you get some error that you can't just have a Boolean flitting here somewhere. So probably that's never going to happen. This is the more likely case, is you write this with one equal sign instead of two. If you ever go on to learn other programming languages like C or C++, then those languages let you do this when normally you probably didn't mean to. So in the other languages, what will happen is 1 would get copied into x, and then it would treat the value 1 as a Boolean, and in this case, anything that's not 0 is true, and so it becomes if true. So those can be really hard to track down in other languages because it doesn't give you any warning that something's wrong. It just does it, but it might not do what you want. So that's one common error. The other, probably the most common error, is using, at least for Java, is using equals equals with strings. And it doesn't work. You can't use equals equals with strings. You can basically should only be using it, well, you can use it with strings, but it probably doesn't do what you want. So here I can give a little bit of background, not a whole bunch, but just a little bit into why it doesn't work. So let's say I have some string variable. I'll just call this one S1. And I have another string variable, and call that S2. And let's say we read in something from the keyboard. So I have a scanner object, scanner keyboard equals new scanner. So if we did something like this, S1 equals keyboard.next. So we read in something, S2 equals keyboard.next. Then what you might be tempted to do is to say, well, I want to see if those two strings are the same. So we might write something like if S1 equals S2, then we do something like system.out.println same. Okay, so this should look pretty harmless, like it probably should work. So imagine we make these two string variables. I'll make a little box over here of my variables. I have an S1 and an S2, and we have a keyboard. We come into this line and we type something from the keyboard. So we type in hi, and so S1 is set to hi. And then let's say we type in hi again for S2. We type in hi. And then what you would expect is you would say, all right, S1 is high and S2 is high, so this should be true, so it should print out same. But in reality, if you do this, that's not what will happen. This will actually be false, and it'll skip down to whatever comes after. So why is it false? So here's the reason. When we make these variables, S1 and S2, the computer doesn't know what you're going to type in and so it doesn't know how much space and memory to store here. So when you have like a regular integer, for example, like you say int x, we talked about how many bytes it uses, and so with an integer it's probably 4 bytes. And so somewhere in memory at like address 10, I'm just making up a name, so like address 10 is going to store x, and then it would allocate like 4 bytes of storage for that variable. And then if you have like another variable y, maybe it's stored at address 14, so it could store another 4 bytes. So it can actually store the number that you want right here in memory. So if the variable x is set to 100, then it would actually store 100 right here. And then for y, if you set it to whatever 6, then it would store the 6 right there at some place in memory. Well, the problem with strings is it doesn't know how long the string is going to be. You know, you could type in hi, or you could type in hello, or you could type in some really long thing. And so in advance, the computer has no way of knowing how much memory should be allocated for this variable. And so what it does instead is when you type in something like hello, it's stored at some other place in memory. Like maybe I'll just make up a place. Maybe it's stored at address 5000. And then instead what's stored here for the string is it really stores like the address of where the real text is stored in memory. So this is like a known quantity. It can allocate enough memory to store an address like 5000. And then for S2, if I typed in hello, maybe that's stored at address 6000. And even though I type in the same hello, what it's going to store here instead would basically be like the address of where that thing is in memory. And so now when we come down here and we say if S1 equals S2, what the computer is really doing is it compares these two addresses and says, oh, 5000 and 6000 are different, so I'm going to skip and just go up to whatever comes afterwards. And then you don't have this problem with numbers like x and y. So like if I change this to x and y instead, if I have these integer numbers, then it's really comparing the 100 to the 6, and then that works fine because 100 and 6 are different. Question?
Yeah. Can you specify exactly which storage chunk you want it to go in? And then if you wanted to test it, you could set the variable to the same address, and then it would be true?
You can. There's a thing called a string buffer that lets you do that. But with the regular string, you can't. It just goes in wherever Java decides to put it. But yeah, there's a different kind. Yeah, when we start talking about objects, then we will be able to have things like point to the same object that we want to. So we're going to do something kind of similar to that later on. All right, so basically we're being told, or I'm telling you, that if you compare strings like this, it doesn't work because it really compares the addresses where the strings are stored, not the actual contents of the strings. And so the way around it is there's a method to do it, and it's called the equals method. And so you would write this instead. You would pick one of your strings, either S1 or S2, and then do a dot, and then the word equals. And then in parentheses, give it the other string to compare to. And so this will invoke some code that someone that wrote Java created. And the equals code will go through and compare every character in S1 to every character in S2, see if they're the same, and if they are, then you get true as a result. So this would actually be true in my case if I typed in hello, and then it would print out same. Equals is case sensitive, and so if one of these was uppercase H, then you would get false. If you wanted to compare without knowing about the case, then there's an equals ignore case call. So it'd be like S2 dot S1. So this would compare S2 and S1, and if they're the same, without any care about if it's upper or lower case, then you get true back. Okay. All right, so I guess I had a little sample, but it's probably not worth running because it would just be exactly what I kind of said here. So, if I typed in the same string, then if I do equals, now it would check the same and you get the same. So Surely common error. I'm assuming you'll probably make the mistake of instead writing S1 equals S2. This will run but not give you any error messages. So if you're getting weird things with comparing strings, then hopefully this will jog your memory that, oh yeah, I'm supposed to not use equals, I'm supposed to use the dot equals instead. Okay, so let's see here. So if there aren't questions there, let me move on to switch statements. And so I'm not going to spend too much time on the switch statement. So the switch statement is another way you can do an if-then-else statement. And some people will never use the switch statement. They'll just always use if-else statements. So you could get by without having a switch statement at all. But you might see other people use it, so it's good to just know what it is. And it is a little more convenient to use if you're trying to do like a really long string of if-elses. So here's the way it works. You have the word switch, and then parentheses you have some expression. And normally it used to have to be an integer number, but in the later version of Java it could also be a string. So you can't use this with a double, for example. So only things that are integers. So that would be like like ints or longs. You could also use it with a char or with a boolean. So it'd work with those, or a string, but it won't work with like a float or a double or something like that. So the way this works is you have the word switch followed by something that's like a number or a string, and then a curly brace. Here's the ending curly brace, and then the word case everywhere. And then after the word case, you have some value. This value has to be a constant. It can't be a variable. And then what Java will do is it'll compare whatever this is to whatever you have here. If these two things are the same, then it's going to run all of this code until it hits a break statement. When it hits the break, then it's going to jump to whatever comes at the end of this curly brace. So what if this thing is not equal to this first expression? So if these are different, then it's going to move on and compare it to the second one. And if these are the same, then it'll go and run all this code until it hits the break statement. Then it'll pop to the end. And if this expression 2 didn't match, then it would compare it to the third one, do the same thing. And then if you like, you can stick the word default at the end, and then this will always run if this expression didn't match any of the ones above it. So basically it's the same as like a bunch of if-elses. And it's a little less typing to do and a little easier to read than a whole bunch of if-else statements, but logically it does the same thing. Let's see here. So if you leave the break out, then Java will just keep on going down until it hits a break or the end. So let's say that this expression matched the first one, then it would run these lines of code. And then if there's no break here, then it would just keep on going and run these lines of code as well. And then finally, when it hits this break, then it would jump to the end. So normally you want to stick a break in there, although in rare cases, you might want it to do this on purpose. So here's a little example. Let me go, I'll type this in. So here is this graphics example. I guess I should delete all this other stuff. Let's get rid of it. Okay. So just as a little example, let's use this with char. How about I'll do it with an int first. I'll just set to something. So I have some variable, and somehow it gets set to some value. In this case, I just set it to 4, but maybe there'll be some calculation or something that happens to make it get the value 4. And if you want to print out different values, different things, depending upon what its value is, I could use that switch. So I could say switch grade. There's my curly braces, and then case, and I could say case 1, and I'll just do system.out.println 1, and then break, case 2, do this. And then case, I'll just go straight to case 4. So I don't have to do a case 3, although it might make sense to do so. And then for the very last one, I don't have to put a break statement. I could stick one there if I want to, but it doesn't really do anything. The break statement will just make it go to the end, but it's already at the end. So if I compile and run this, then it outputs 4. So it just compares the value grade, which is 4, and it's not 1, it's not 2, it is 4. So then it runs this chunk of code. And if I change this to something like 2, and then here it's 2 is not 1, but it is 2, so it runs this and then hits the break and then jumps to the end. And if I didn't have this break statement here, then when it matches with the 2, it's going to print out 2, but then keep on going. So it should also print out 4, and then it doesn't stop until it gets to a break. So here I get both 2 and 4. So once in a while you want to do that on purpose if you happen to want to run code from two different case sections, or more than 2. And then here just briefly I can do this with chars as well, since char is considered an integer type. And with chars you put them in single quotes. So in this case here I had grade set to B, and so it should match this case right here, print out good. In this example I have the break commented out, so it should print good and then also print pass after it. So there's good and pass. So basically it's an if-else statement, but it's a little cleaner to look at in the switch format. Okay, so any questions about the switch statement? So you can use it if you like. I don't think I'm not going to give you any questions where I specifically say you have to use the switch statement though. All right, so the next topic is random numbers. And we need random numbers for all sorts of things. If you've got like a game, for example, and you want things to be different each time you play, then you need to generate some random numbers to make it different. Whatever, you've got a deck of cards or something, you want to shuffle it, or you just want some different behavior, or you're doing some simulation. So random numbers are pretty important in all sorts of programs. In our case, what we're really dealing with aren't truly random numbers. More accurately, they're pseudo-random numbers. So this means they're kind of random, but not really random. But they're random enough that they should do the job. In our case, what this basically means is that there's an equal likelihood, an equal probability so in our case, this means there's going to be an equal chance that if we specify a range of numbers, like give me a random number between 1 and 10, that any number from 1 through 10 is equally likely to pop up. However, what makes it pseudo-random is there's actually a function, so that if we knew the function, we would know exactly which number is coming next. So obviously that's not random if you could know exactly what number is coming next. So basically, as an example of one of these functions, consider this as our function. Let's say our function is r equals, let's do this one. So let's say this is our secret function. To get the next random number, I plus 1, to get the ith plus 1 random number, take the ith random number, or take the previous random number, multiply that by 7, divide by 11, and then compute the modulus, the remainder. So we'd start with an initial random number. So let's say that r sub 1 is just the number 1. So this is called the seed value. It's the first value. So now let's say we ask the computer, give me a random number. And so we go to our formula. To get the random number, you take the current one. To get random number 2, you take random number 1, multiply that by 7. So current value is 1. And then compute the remainder with 11. So 11 goes into 7 0 times with the remainder of 7. So for your first time, you get 7 as your random number. And then let's say we want to get a random number again. And so to get the third random number, you take the previous one of 7, multiply that by 7, which is 49. Divide that by 11 and get the remainder. And the remainder is 5. So our next random number is 5. If we ask for another random number, we take the previous one of 5, multiply that by 7, which would be 30, do the modulus 11, and then we end up with 3. If we do this again, we get 3 times 7 mod 11. That gives us 10. So if you didn't know any better, you get 7, 5, 3, 10. You know, it looks like the numbers we're getting out are kind of random, and we'll end up with something that's pretty uniform from the number space from 0 up to 10. Okay, so obviously it's not really random, because if you know this formula and you know what the previous random number was, then you can figure out what the next random number is. But for most of our purposes, this is good enough. Not this exact function, but this idea is good enough to get sort of pseudo-random numbers. One way we can make this a little more random is by starting with a different seed value. So if you always start with 1, you're always going to get the same sequence of numbers out when you ask for a random number. And so what we'll typically do is we'll change this based on the value of the computer's clock. So with most clock times, you can get the number of milliseconds that have elapsed since something like January 1st, 1970 or something. There's like that's like the date of Unix time, when this algorithm began. And anyways, so we can usually get the number of seconds since this date in 1970. and use that number as the value to seed the random number generator. So if we have like a different value here for this initial seed, then you get different sequences of numbers out. So that'll make it look random if you run this at different times. So we'll do that approach, and Java actually does that for you automatically. But if you want to, you could specify the seed value, especially if you want to get the same number sequence out for some purposes of recreating your random numbers. Okay, so how do you do this in Java? So that's like the idea behind generating random numbers. To actually do this in Java, at the top you add import java.util.R random. There's another way you can get random numbers using the math class, but we won't go that way. This way is a little better. So this is at the top, and then somewhere in your program you make a variable of type random. And you set it equal to a new random, and then parentheses. So kind of like how you made the scanner object, where you said scanner keyboard equals new scanner. Here's kind of the same thing. We're saying, let's make a random object. Here I'll call it ran generator. There's not supposed to be a space there. And then set it equal to a new random. Once you've created this thing, this is like a random object that you can use to get random numbers from. Then we can do things like int r equals rand generator dot next int n, and so this gives you a random pseudo-random number that's from 0 to n minus 1. So if n is 10, this would give you a random integer that's 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, but you wouldn't get 10. So that's important that this is like one more than the last random number you'd like to get. And then if you wanted to get like a double, you could do this. You could say double D equals rand generator dot next double. And then just give it parentheses. This gives you a random number that's from 0 to 1. It's always going to be less than 1. It's possible it could be equal to 0, although highly unlikely. But it's theoretically possible to get 0, but you'll never get 1. The biggest you would get would be 0.9999999. What if you didn't want a double between 0 and 1? Then you can multiply it to get what range you want. And so if you did this and said like d equals d times 5, then now you have a random double that's between 0 and 5. So you can just multiply to get whatever range you're interested in using the double. Okay, so let's do a little example. I'll go back here to Dr. Java. So we add at the top import java.util.random. We add in here our random. Let me get rid of this switch stuff. So we could put our random right here. Random RND generator equals new random. If I put it here, I can only use it inside main. So we'll say a little more about this variable life stuff later, but another thing I could do is I could stick it up here instead. And I guess for now, maybe it doesn't matter too much because we haven't talked about really making our own stuff outside of main. But when we do, it would make sense to put your random generator up here because you only need to make one for your whole program. So if you stick it here, then you can use it in other places. So anyways, we'll do that later, but just to mention that now, I'll leave it inside main for the moment. But in the future, you might stick it up here instead. Okay, so here in this little example, let's just simulate flipping a coin. And the way we could simulate flipping the coin is get a random number that's either 0 or 1. And if the random number is 0, then that'll be like flipping heads. And if it's 1, then that would be like flipping to tails. So here I can say, let's see here, coin flip equals R&D generator dot next int. And then if I give it 1, will this work? Anybody? So this will kind of work, but not really, because if I said 1, this gives me a random number that's less than 1, doesn't include 1, so all I could get is 0. So I really have to stick 2 in here, and then that gives me a random number that's either 0 or 1. And then I could do an if statement. If coin flip equals 0, then I'll just say heads, else so that's all we need for like one coin flip. So if we run it, so we got tails, I run it again, I get heads, run it again, I get tails, then heads, then tails, tails again. So it looks like it's giving us random heads or tails, with about 50% either time being heads or tails. Okay. So any questions so far? So let's do a little program that kind of ties together a lot of the stuff we talked about so far. And that's this Monty Hall game show problem. So some of you might have seen this before. It was in, where was it in? It was in that Parade magazine insert that's in the Sunday paper, where Marilyn Vos Savant, who has whatever, IQ of 200 or something, supposed she's the smartest person on the planet. This was like one of the little puzzles in her column. So here's how it goes. So imagine you're a game show contestant, and you are placed, before you are placed 3 doors, door 1, 2, or 3. And behind one of the doors is $1 million in cash. You don't know which one, but one of those doors has $1 million. And then the other 2 doors, they have the consolation prize of whatever, a box of macaroni and cheese or something. And so you get to pick a door. The way the game goes is you pick one of the doors. So let's say you pick door number 2. And then the game show host says, well, door number 3, I'm going to open. So the game show host picks a door that doesn't have the $1 million behind it. So obviously, at least, so if this had the $1 million, then the host could pick 1 or 3. If 1 had the $1 million, then the host would pick 3. If 3 had the $1 million, then the host would pick 1. So the game show host picks a door that doesn't have the $1 million, like door 3, and says, here I revealed door 3, it has the macaroni and cheese. So now you have the choice. Do you want to stick with door number 2, or would you rather change to door number 1? So in the Monty Hall problem, you're asked, well, should you switch or stay, or does it matter? So how many people think it doesn't matter? There's 2 doors here. You have a 50% chance either way. So who cares? Anybody? No one thinks it doesn't matter? Okay, so how about who would want to stay on the door you picked? At least one person. Who would want to switch? So 4 people want to switch. Okay, so You have people that would do nothing, which in this case I'll take that means you're going to stay with your door. So, but the majority said you'd switch. So, well, there's some statistics we could work on to kind of answer this. But another way we could address this would be you could run it in person. You could actually have your friend do this, and then you pick the door and do it a bunch of times, and then see if it's better for you to stay or switch. But if you don't have a friend to help you, then you could write a computer program to be your friend and then count how many times you won if you stayed or switched. So let's do that. Let's write a computer program that can simulate this problem, and then we won't have it count the wins. We'll just count the wins in our minds. Although we could have it count the wins if we wanted to be a little fancier. So here's what we'll do. We'll have 3 doors, 1, 2, and 3. We can make a variable called prize and set it equal to a random number. That's 1, 2, or 3. So that's the first thing we'll do, is we'll pick a random number that's 1, 2, or 3 to represent one of these 3 doors where the prize is. Then we'll ask the user to pick a door. So we'll make a variable, let's just call it pick 1. And we'll input this from the user. So we'll just input, pick a door, 1, 2, or 3. The user types in a number. And whatever the user types in, we'll store in pick 1. Then the next thing we'll do is we're supposed to reveal a door that doesn't have the prize behind it, and it's not the pick. So we need to find a door that's not the prize and not pick 1. So we can do that just kind of by brute force. We could just start with door 1 and say, well, if 1 is not pick 1 and 1 is not the prize, then open up door 1. And then we could do the same thing for 2, and then else the last one would be 3. So we could do that with a little brute force. In this case, actually, if I did it systematically, that would give away a little information, but we won't worry about that. Because if you know that you're checking door 1 first, then it could tell you something if the prize might be behind one of the other doors. So we'll just find a door that's not the prize and not the pick, and then say, door whatever doesn't have the prize. And then we'll just ask the user to pick another door. So we'll say pick 2, we'll input that. And then pick 2 could be the same door, or it could be the other remaining door that wasn't revealed over here. And then the last thing we would check would be we do like if pick 2 is the same as the prize, then you win. Otherwise you lose. Well, if you don't really lose, you still get your box of macaroni and cheese, so you get something. Okay, so that's our strategy. So let's see if we can write this up in our program. So let's get rid of these guys. So I'll leave my random generator here. And the variables I had were a variable for the prize, and a variable for the first pick, and also for the second pick. I'll do it this way. So, just a few welcome messages. So we'll read in the first. I need to make a scanner object. So I need to import java.util.scanner. Before I pick a door, let's pick the door behind the prize. So I'll say prize equals ran generator dot next int 3. So if I do 3, this would give me either 0, 1, or 2. If I wanted to make that 1, 2, or 3, then I could add 1 to it. Or I could really have just left it as 0, 1, or 2 if I wanted to. So anyways, I'll just make it so it's 1, 2, or 3. So there's our random number right here. We read in the player's pick. So pick 1 gets set to keyboard.nextInt. So now we need to open up a door that's not the player's pick and it doesn't have the prize. And there should always be one, since you got 3 doors and 2 choices that we've made. So here I'll just start with door number 1. So if pick 1 is not equal to 1 and prize is not equal to 1, then I can go ahead and safely reveal door number 1. Otherwise, I can check door number 2. Oops, prize. And then lastly, if it wasn't door 1 or 2, then it would have to be behind door number 3. So I don't even need to bother putting the else if. I can just say else and just always fall into this case. So the only way we could display this one would be if like the prize was behind 1, the player picked 2, then 3 would be the remaining one, or vice versa. The player picked 1, the prize was 2, and then the player picks 3, or then we'd reveal 3. Okay, so we just revealed one of the 3 doors that doesn't have the prize, and then we asked the player to switch or to stay, or in our simpler version, just pick a new door. And I'll call that pick 2. I could just have used the same variable, I guess, but I'll use pick 2. And so now we just check if the person won. So if pick 2 is equal to the prize, you won $1 million. Otherwise, you won a box of macaroni and cheese. The 1 million, or I'll just say the prize, was behind door number prize. Okay, so does it seem like that'll work? So let's compile it and see what errors I made. I forgot I put a colon instead of a semicolon. And that's it. So let's see if it works. Let's move this up a bit. So pick a door. So I'll just pick door number 1 all the time. And then door 2 is revealed. And then how about I'll do this 10 times and I'll just stick with the same door. So I stuck and I won $1 million. Try it again. Oops, I need to recompile. So 1 and 1, I won again. This time I lost, so that's 2 out of 3. 2 out of 4. 2 out of 5. Started out good. 2 out of 6. 2 out of 7. And 2 out of 8. So I started out on the streak, but sticking with the same door, I only won 2. Well, I'll do it 2 more times. 2 out of 8. So 3 out of 9. Whoops. So that was 4 out of 10 times. So that's pretty close to 50%. What if I always switch? So I'll start with 1 and go to 3. So that's 1 out of 1. And now it's 2 out of 2. And 3 out of 3. And 3 out of 4. 4 out of 5. 4 out of 6. 4 out of 7. 5 out of 8. 6 out of 9. And so 7 out of 10. So 7 out of 10 times I won by switching. And 4 out of 10 I won if I stayed. So out of that little sample, it looks like it's better to switch. And in fact, if I ran this more times, then I should win if I switch about 2/3 of the time. And then I should only win if I stay 1/3 of the time. So here, if you think about why that is, initially, when you make your choice, so initially there's like a 1/3 chance the prize is behind one of these 3 doors. And when you pick one, let's say you pick this one, there's a 1/3 chance your prize is behind the door you picked, but there's a 2/3 chance the prize is behind one of those other 2 doors. And so now when the game show host reveals like one of these doors isn't the prize, you still have a 2/3 chance that your prize is behind one of these doors, but you know it's not this one, it has to be that one. So if you switch to the other door, you have a 2/3 chance, but if you stay with your first door, you've only got a 1/3 chance. Even though it seems like you should have a 50% chance because there's only 2 doors, but you actually have a better chance if you switch. On the other hand, if the game show host cheats and after you pick and open up a door, if the game show host swaps around where the prize is, then you're back to a 50% chance. So here, we made a little simulation of the game, and if we wanted to get fancier, then we could have remembered how many times we won or lost, so we could calculate the probability for us. Okay, so any questions so far? So there's an example of using random numbers with stuff we've learned so far, if statements and variables and Boolean expressions. So let me just introduce the next topic and then I'll stop. And so the next topic is loops. So right now we've had it so our program pretty much just runs once and exits. And it might make a decision along the way, but it just goes and then quits. And so pretty often you want your program to repeat something more than once. And to do that, we have various ways we can have loops. And so a loop is where you just repeat some chunk of code more than one time. And in most programming languages, you have multiple ways to make loops, and Java is no exception. We have basically three kinds of loops we can use. There's the while loop, there's the do while loop, and then there's the for loop. And all three of these loop types can be made to be equivalent. So if you're trying to write the minimalist language, you would just pick one of them. But basically, the while loops are good for repeating something until some condition happens. Like you keep repeating until you win the game or lose the game or something like that. That's normally where you'd use these while or do while loops. The for loop is normally used for counting, but it doesn't have to be. So if you're going to do something 1,000,000 times or 50 times or X times, then normally you'd use a for loop. But once again, you could use a while loop instead, so you can use them interchangeably. But this is like the typical ways, the typical scenarios where you'd use one loop versus the other. So let's just start with the while loop, and then I'll give you an example, and then I'll stop for the day. So the while loop is real simple. You have the keyword while, and then inside parentheses you have something that's a Boolean. So just like an if statement. And what will happen is Java will come in here. If this Boolean is true, then it's going to run whatever is inside its curly braces that come after it. And then when it gets to the bottom, it goes back up and checks again. If this is still true, it'll go run this code. And so it'll just repeat running this code here over and over again until finally this becomes false. And how will this become false? Well, normally there'll be some line of code in here that makes this false. If there's something in here that never makes it false, then this thing would just loop forever and never stop. That's called an infinite loop. And when that happens, your program will just freeze up. Generally, it'll just stop, and then you can't do anything, and you just have to kill your program. So here, I'll just show you that to you real quick. Let's see here. Leave that. So if I say while, let's see, int x equals 3. So if this is my program, I set x to 3, and then say while x equals 3, well, that's true since 3 is 3. It's going to just print out x, and then I'll come back up here and x is still 3. So this will just loop forever because x is always 3. So if I compile this and run it, then here in this window, I just see like a bunch of 3s being spit out as it goes around in this loop, and I'll just do that forever until I stop the program. And I stop it by doing, I forget how to stop it now. If I do reset, yes. So here in this case, if I do reset, then it stops. And in NetBeans, there's a little stop button, like on a, VCR or something. It's got a little square stop button. So generally, if you get these infinite loops, then that's usually not what you want, and you have to stop it. So normally, there's some condition in here that makes it so that makes it so this loop eventually stops. So here's a typical thing. So let's set x to, how about if I do this instead? So here I start x at 3, and then while x is bigger than 0, which it is, then we print out x, and then here this changes x, so we subtract 1 from it. So then the next time this goes through, x would be 2, and then it would be 1, and then finally x would be 0. And then when x is 0, 0 is no longer greater than 0, so then that stops the loop, and then it will come and exit. So if I run this, then here it's output 3, 2, 1, where the first time through, it print out x is 3, x gets subtracted to 2, 2 is still bigger than 0, so it prints 2, now it's 1, 1 is bigger than 0, it prints 1, x is 0, 0 is not bigger than 0, it stops. So I could easily, if I wanted to print out the numbers from 10 down to 1, I just change this to 10. And so now it outputs everything from 10 down here. Whoops, if I scroll up. So that's the basics of the while loop. And then if I wanted to repeat something, like if I didn't want to print out x, but I just wanted to print out like whatever 10 random numbers or something, then instead of printing out x, I'd do that. I'd print ran generator dot next int. How about 10 plus 1? So this would give you a random number that's from 1 to 10. In this case, 10 of them. So here I got numbers ending in 4, 1, 10, 6. And this time in 8, 5, 5, 7. So whatever code you want to run multiple times, you can put into a loop, and it'll run whatever's inside there until this condition becomes false. Okay, so that's the idea behind the loop. So any questions? We'll do some more of this tomorrow, but that's the basics. Yeah.
We do all x is greater than a random number, so you don't know when it stops.
Yeah, we could certainly do that too. And then, yeah, you wouldn't know when it stops. It would just go until, yeah, until that happens. Any other questions? Okay, so the loop part, not on our little test tomorrow, but it will be for the drill. So the drill tomorrow is asking you to do some stuff with loops. So we'll say more about loops tomorrow. So otherwise, I'll let you work on the drill and let me know when you're ready.